Hi, this is Sir Aris. Let us talk about geometric series. So for a geometric progression, it is defined as a collection of terms where each term is multiplied by a fixed number to get the next term. For example, if you have 2 and then the next term is 4, 4 is derived by multiplying 2 with 2. So multiplying 4 by 2, we get 8. Multiply that by 2, we get 16. 16 times 2, that's 32. So another example, if you have 1 and then 2/3, multiply 2/3 by 2/3, you get 4 over 9 times 2/3, that's 8 over 27, times 2/3, 16 over 81. So generally, we can write it as A as the first term, the next is AR, the third is multiply the second one with R, so AR squared, and AR cubed, and so on, as long as R is not equal to 0. So by adding each term in a sequence, we have an infinite series. And our task is to get the sum if it exists. So for an infinite series derived by adding the terms in the third example, you have A plus AR plus AR squared plus AR cubed, and so on. Um, for series whose terms form a geometric progression, we call it a geometric series. Now let us define the partial sum. So for the sum of the first n terms of a series, we call that, or a progression, we call that the partial sum, given by this expression Sn, defined as A plus AR plus AR squared plus AR cubed plus AR to the n minus 1, where AR n minus 1 is the nth term. We can simplify the expression for Sn. We can do that by subtracting SNR from Sn. So let's list down. So Sn here is given by this expression. SNR, so we'll multiply both sides by R. So we get SNR. Here you have AR squared, and so on. We subtract this equation from this equation. So you have Sn minus SNR. You have A here minus AR, but AR here cancels with the positive AR at the top. Also, AR squared cancels with AR squared, AR cubed cancels with AR cubed, and so on. But we are left with, so the only term that doesn't cancel out is ARN. So we have minus ARN. Or we can write Sn as A times 1 minus Rn divided by 1 minus R. So the sum of the geometric series can be written as S equals the limit of Sn as n approaches infinity. For this geometric series, we can find a sum if and only if this R, the absolute value, is less than 1. We can see it easily that if R is greater than 1 or less than negative 1, this value keeps on increasing. The magnitude keeps on increasing, so Sn will not tend to Sn will just have a non-zero value or increasing as n goes to infinity.